Thank you for attending this presentation. Today we'll be discussing the theoretical and applied treatment of hydrogen bonding in alcohols utilizing Fourier transform infrared spectroscopy. Thermodynamic models are critical to use in industry. It may be applied to predict the phase behavior of chemical mixtures. However, alcohols and other materials that self-associate have historically provided unique challenges to modeling in relatively poor fits. Our group seeks to use quantum mechanical simulations and spectroscopy in line with thermodynamic modeling to achieve a better outcome. This work will focus on the categorization of the spectra in order to determine model parameters. Hydrogen bonds may be classified into several different types. Veritime's theory assumes a linear association model, where each alcohol has one donor and one acceptor site. Now, the hydroxyl stretch can be categorized into alpha, beta, gamma, and delta bonds. Where the alpha and beta are free hydroxyls, the delta is in the middle of a chain, and gamma makes up one end of the chain. The alpha and beta free ends may be represented as a fraction of total molecules, defined as XA, or fraction free, equal to number of moles that are free over number of moles total. FDR data is collected on N-butanol and cyclohexane with a variety of concentrations and temperatures ranging from 30 degrees Celsius to 60 degrees Celsius. Shown here is a 15% raw spectra, and across the wave number range, there is a noticeable change in area as temperatures varied. Once collected, the spectra must be cleaned and scaled. Scaling is accomplished through Beer's law, shown on the right, where absorbance equals a molar extinction coefficient multiplied by path length and concentration. This may be solved for concentration. Cleaning requires the removal of the background done by the instrument, as well as the solvent and the cell effects, which are taken separately prior to recording a sample. Shown here is a scaled spectra of 15% N-butanol. Compared to the previous raw spectra, this is significantly smoother as the cell and solvent effects have been removed. Additionally, scaling has been accomplished that amplifies the leftmost peak in relation to the rest of the wave number range. Species in infrared spectroscopy show up as a distribution across wave numbers. The Voigt profile shown here is a convolution of the Gaussian and Lorentzian distributions. In the equation for the Voigt, absorbance is dependent on the height of the peak, h, a Lorentzian width, L, the curved center, C, and a Gaussian width, G. A total of 5 Voigt peaks are used to capture the hydroxyl stretch and are optimized through a nonlinear least squares function. The free end peak, occurring at 3650 wave numbers and made up of alpha and beta hydroxyls, uses 2 Voigt functions to capture a shoulder due to conformational isomers. Integrating each curve gives the apparent concentration attributed to each species. Once bond concentrations have been established, analysis and predictions may take place. In the figure on the top right, fitted peak centers are plotted. Each color here represents the corresponding bond type. You can see that as temperature, represented by the various shapes, and mole fraction on the y-axis, are varied, there is a noticeable redshift at low concentrations, followed by a vertical trend. The following 2 plots show the application to the RTPT thermodynamic model. This model derives bond type concentrations directly by using the fitted free end fractions and utilizes 2 equilibrium constants, one that goes from monomer to dimer and one that goes from dimer to polymer. The figure on the left shows the dilute region under 3.5 mole% N-butanol, while the figure on the right shows the entire experimental region. You can see that the X's, or the experimental data, follow the predicted RTPT lines throughout the concentration range. Additionally, we may determine the chain length of N-butanol polymers. You can see that as mole fraction increases, the average chain length also increases as there are more molecules in solution. While as temperature increases, the average chain length decreases as there is more kinetic energy and long chains become less favorable. In conclusion, fundamental chemistry, through spectroscopy, may guide thermodynamic model parameters by fitting the hydroxyl stretch and FDIR with a series of Voigt functions. These Voigt functions are attributed to different types of hydrogen bonding through Veritime's theory. And hydrogen bonding in alcohols has strong trends as temperature and concentration are varied.